Welcome to video series on influence line diagram for indeterminate structure, in which we are learning how to draw ILD for various functions of two-span continuous beam. In this video, you will learn influence line diagram for interior support moment of continuous beam using Muller Breslau principle, for which we will be considering two-span continuous beam, and we are interested to know how to draw influence line diagram for support moment at B and how to get this influence line diagram shape. So let us start. So consider this continuous beam ABC. Span AB is equal to 4 meter and BC is equal to 6 meter. And we are interested in finding the ordinates of influence line diagram for interior support moment at B at 1 meter interval. And here we are going to use Muller Breslau principle to draw the influence line diagram. So before we start, let me tell you that though these supports look similar, there is difference between this support and this support. The end support, at end support bending moment is 0 because it is a simple support, whereas support B is a continuous support. It is continuous beam, and here there is negative bending moment if the load is downward on this beam. If this beam is subjected to downward load, then hogging bending moment will develop at B. And now we are interested to know how to draw influence line diagram for this bending moment at B. If you want to understand basic concepts related to influence line diagram and what is Muller Breslau principle, then please watch my previous videos. So in this video, we will learn how to draw influence line diagram for bending moment at B. For this, let us consider this beam. Now we know that by Muller Breslau principle, if you want to draw influence line diagram for any function, first of all, we have to remove the ability to resist that function. So here we are drawing influence line diagram for bending moment, and therefore we have to remove the bending moment carrying capacity at that section. So let us see how we can do this. So to draw ILD for a support moment at B, remove the ability to resist movement at B by introducing hinge as shown in figure. So here we want to remove its bending capacity, and therefore we will introduce hinge there. And then we will apply unit moments at B. Now when we apply the unit moment at B, let us see what shape we can get. So when we apply unit moment, hogging moment here, because here the moment is negative, and therefore we are applying the unit moments like this, and because of unit moment, the beam will deflect as shown in this figure. And this deflected shape of beam to some scale represent ILD for bending moment at B. Why to some scale? Because here actually what Muller Breslau principle says, you have to make rotation equal to 1. But we don't know what is the moment required to make rotation equal to 1. Rotation means change in slope. So we have to make change in slope here equal to 1. But initially we don't know how to, what moment should be applied to make the change in slope equal to 1. Therefore we are applying unit moment. And since we have applied unit moment in place of unit rotation, this is the shape. It is similar to influence line diagram of moment at B. But when we make this slope here or rotation here equal to unity, then it is called as influence line diagram for bending moment. So the same diagram can be used as ILD if we make the rotation at B equal to 1. And you know that we are solving these problems using conjugate beam method, because here in Muller Breslau principle we have to draw the deflected shape, and for drawing the deflected shape we are using the concept of conjugate beam method. So here to make the rotation equal to 1, to get unit rotation, that is change in slope equal to 1, make change in shear force at that section of conjugate beam equal to unity, because we know that the relation between conjugate beam and the original beam. the slope in original beam is equal to shear force in conjugate beam, and deflection in original beam is equal to bending moment in conjugate beam. And therefore here, to have unit rotation at B, we have to make change in shear force at that section equal to unity. And what is that shear force? How to make that one? Shear force in conjugate beam, rotation in original beam, and therefore shear force at that section we have to make equal to 1. So let us see how to make this shear force equal to 1 in conjugate beam. So first of all, we will start with a basic thing, that how to convert the original beam into conjugate beam. So to draw influence line diagram for support moment at B, we have to divide all the ordinates of deflected curve due to unit moment by change in shear force at B. Please remember this, because change in shear force is equal to rotation in original beam. That is reaction at hinge support at B of the conjugate beam. We will understand this while solving the problem. So this is the given beam and we are interested in knowing the deflected shape or influence line diagram for support moment at B. So by Muller Breslau principle, first of all, we remove the bending capacity at B by introducing hinge there. And then we apply unit moment in the direction of that moment. Since it is hogging moment, the direction of the moment, unit moment will be like this. And because of this, this will deflect like this. And now we are interested to know this deflected curve, various ordinates of this deflected curve for this beam. That means now we are interested to know what will be the conjugate beam for this case. We will be solving the conjugate beam for this beam. And you know that conjugate beam is nothing but it is an imaginary beam which is loaded with M by EI diagram of original beam, and therefore we have to draw bending moment diagram for this beam. Once you draw the bending moment diagram for this beam, that will be the load on conjugate beam, and then you have to modify the support, and if you calculate bending moment at any section of conjugate beam, you will get ordinate of deflected curve of this original beam. So let us first see how to draw the conjugate beam for this case. So we have removed the bending capacity of at section B by introducing hinge here, and now we will see how to draw the conjugate beam for this. We know that M by EI diagram of original beam is load on conjugate beam. So we will consider 1 upon EI is equal to K. As I told you that we are drawing conjugate beam for this case. So to draw conjugate beam, it is an imaginary beam which is loaded with M by EI diagram. So therefore we have to draw the bending moment diagram for this case. To draw bending moment diagram, first of all we have to calculate the reactions at the support. Then only we can calculate the bending moment. So therefore we will consider first portion AB, and then we will calculate what is reaction at A. Since this beam has hinge here, we can apply the condition that bending moment at B equal to 0. So for that we have drawn the free body diagram for this portion. This moment of 1 we have applied here, it is anti-clockwise moment. So we have shown like this, and now we will apply bending moment at B equal to 0. Bending moment means taking moment of all the forces from one side. And therefore we can write RA into 4 is equal to 1, and therefore we get RA is equal to 1 by 4. Now we have calculated this RA. Once we calculate this RA, we can calculate bending moment at all the sections. Let us see how to calculate bending moment, because we want to know what is the loading on conjugate beam. So load on conjugate beam is equal to M by EI diagram of original beam. This reaction is 1 by 4. So we know that at simple support, bending moment at A is equal to 0. Similarly, bending moment at C is also 0. What is bending moment at B? Bending moment at B just to this left of this section is 1 by 4 into 4, which is equal to 1. and after that these moments will cancel each other. So at B we have bending moment of 1. So therefore we know the bending moment at A 0, bending moment at C 0 and bending moment at B equal to 1. Therefore we can draw the bending moment diagram. So load on conjugate beam at A is equal to 0, at B is equal to 1K upward. Why upward? Because the bending moment is sagging bending moment. This reaction is upward. You know that due to upward forces, bending moment is always positive. Positive means sagging. And therefore load on conjugate beam is upward. And this load varies linearly. Once we decide what is the bending moment at various sections, we have to modify these supports in conjugate beam. So we have already seen that how to modify the supports in conjugate beam. Roller and hinge supports remains as it is in conjugate beam. Fixed supports become free and free becomes fixed. Interior support becomes interior hinge and interior hinge becomes interior support. So let us see how to draw the conjugate beam. So in this case, we have to modify the support conditions for the conjugate beam. So simple support at A and simple support at C remains as it is. Interior support at B means this support becomes interior hinge, means this. Then interior hinge at B becomes interior hinge support in conjugate beam. So let us see how to draw. So we are drawing conjugate beam for this case. So this simple support remains as it is. This simple support remains as it is. This red dot means this hinge becomes now a support, which is shown by red arrow here. And this blue, which is a support initially of original beam, becomes hinge. So internal hinge becomes internal support and internal support becomes internal hinge. So the support condition look alike, but it is this hinge which has become support and it is this reaction which is now hinge here. And this is the bending moment diagram, which is nothing but the load on the conjugate beam. So here it is 0 and here it is 1. So this is how to draw the conjugate beam for this case. So once you draw the conjugate beam, you know that you have to write the general equation of bending moment at any section, because bending moment is deflection in original beam and we are interested in drawing the deflection in original beam, and therefore we will be writing the bending moment equation at any section for portion AB and for portion CB. But for writing the bending moment equation, first of all, we have to calculate reactions at the support of conjugate beam. So here we have three reactions, RA, RB and RC. So we know that whenever there is hinge in the beam, then we can always apply the condition bending moment at that hinge equal to 0. So bending moment means taking moment of the forces from one side only. And therefore, first we will apply the condition bending moment at B equal to 0. So first we will consider left part of this and we will calculate RA. So taking moment about B equal to 0, RA into this distance is 4 meter and moment due to this triangle is half into this 1K into 4. This is the load. Load means area of this triangle and then distance between this CG and this where we are taking the moment, which is 1/3 of 4 is equal to 0. If you calculate this, you will get negative value, which is 2/3K. So negative, therefore, the reaction at A is equal to downward. Similarly, we can take condition that bending moment at B equal to 0, consider right portion and calculate RC. So in similar way, consider portion, this CB portion, and bending moment at B is equal to 0, RC into 6. This is 6 meter. So moment of this and moment of this triangle, that is RC into 6 plus half 1K into 6 This is the load on this triangular portion, which is area, multiplied by 1/3 of 6 means 2 meter. And if you calculate this, you will get negative value. RC is equal to 1K, and negative means downward. So now we have calculated RA and RC by considering bending moment at B equal to 0. Now we want RB. So RB we can calculate by taking summation of vertical forces equal to 0. So here we have calculated RA 2/3 of K and RC 1K, which is downward. Now apply summation of vertical forces equal to 0. Consider this complete beam, and if you apply this RA plus RB plus RC plus area of this complete diagram, that is half 1K into this is 10 meter. And if you apply this condition, you will get RB is equal to 3.333 K, which will be negative, and therefore negative means downward. So this is how to calculate the reactions at support of conjugate beam. Once you calculate the reaction, next step is to write the general equation of bending moment for this conjugate beam. Now let us write general equation of bending moment for portion AB. We know that all the reactions are downward. So at any section X from A, what is bending moment? It is this force into perpendicular distance plus this force into distance of its CG from the section. So first of all, we will write this relation y upon x. Suppose this is y upon x is equal to 1K upon 4. So from this we get y is equal to 1/4 K into x. So bending moment is equal to, due to this reaction, this is downward reaction, so it is minus 2/3 K into x, and due to this triangular portion, area of the triangle half base into height y, here y is 1/4 kx, multiplied by distance, that is 1/3 of x. So this is the equation of bending moment for any section in between A to B. If you simplify this, you will get this equation, 0.667 kx negative plus kx cube by 24. So this is general equation of bending moment in portion AB. Similarly, we will write general equation of bending moment for portion CB. So to write the equation in portion CB, we will measure x from C. This is our origin and we are measuring distance from C. So we will calculate first what is relation between y and x. So y by x is equal to 1K upon 6. This distance is 6 and therefore this is 6. So y is equal to kx upon 6. Now we will calculate equation at this section. So it is equal to this reaction multiplied by distance plus this force multiplied by its distance from the CG. So if you write it, we get this is minus, because this reaction is downward, minus K into x, plus this is the area of this triangle, half base into height, multiplied by 1/3 of x. So if you simplify this, you will get these equations. Now these are the bending moment equation. When you substitute value of x, you will get the bending moment at respective section, which is equal to deflection in original beam. So we have derived these two equations. This is equation for portion AB and this is the equation for portion CB. Now what we are going to do here, we have to substitute the value of x, which is measured from A in case of AB, that is 1 meter, 2 meter, 3 meter and 4 meter, and calculate respective value of bending moment. Similarly for portion CB, we are measuring from C and therefore we will get value at 1 meter interval. So we will solve this in tabular form. So let us write the table and calculate the value of bending moment at respective section. So once you calculate the value of bending moment section, what you are going to get? You are going to get these ordinates at 1 meter interval due to this unit movement. So let us calculate first the ordinate due to unit movement, and after that you have to make rotation equal to 1. That means change in shear force equal to 1, and here shear force changes due to this reaction, and therefore you have to divide all the ordinate by RB. So here we are going to divide whatever ordinate we will get, bending moment ordinate, that by RB to get the ILD ordinate. So let us see how to calculate this. So to get ILD ordinate at B, to get unit rotation at B, this is not to get ILD ordinate at B, it is to get unit rotation at B, we have to divide all the ordinates by RB, and RB is 3.333 K. Now to calculate these ordinates at 1 meter interval, we will substitute x is equal to 1, 2, 3 and 4 to get these ordinate of bending moment. So here we will take section at 1 meter interval and we are using the equation of for portion AB with origin is equal to origin as A. So distances as 1, 2, 3, 4. So if you substitute this in equation of portion AB, you will get these ordinates. And to get the ILD ordinate, we have to divide all these ordinates by RB, which is 3.333. So if you divide all these ordinates, you will get the ordinate of deflected shape due to unit movement. Similarly, you can use the equation for portion BC, considering C as origin. That means you are measuring the distance from C. So if you write this and substitute x value as this 5 meter, 4 meter, 3 meter, 2 meter, 1 meter and 0, you will get these ordinates. So you have to divide this by RB to get the ILD ordinates. Once you calculate all the ILD ordinates, you can draw influence line diagram for moment at B. Now we can draw the respective ordinates here and we can plot this shape, and this is nothing but the influence line diagram for moment at B. Now you can observe here all the ordinates are negative. All the ordinates are negative. That means if the load is anywhere between A to C, there will be hogging bending moment at B. There will be negative bending moment at B for all the position of load from A to C. Now what is the use of this diagram? So from this diagram we can say that to have the maximum value of bending moment at B, we have to apply the load on this span AC, complete load from A to C. If there is a UDL of for portion A to C, then that UDL multiplied by this area will give you the bending moment at B. And we can say that there is always negative bending moment at B if the load is downward. Now suppose the load on this beam is say 100 kilonewton, point load is there, then due to this case, how we can calculate bending moment at B? So without analyzing this beam, we can directly calculate what is the bending moment at B from this diagram. This is 100 multiplied by this ordinate. So 100 multiplied by minus 0.3 is 30 kilonewton meter is the hogging bending moment at B. So this is the use of this influence line diagram. If you find this video useful, please invest 1 minute to subscribe my channel. Since I am taking a lot of efforts to share you structural engineering knowledge as simplified way as I can. In next video, you will study the application of Muller Breslau principle for drawing influence line diagram of some other function of continuous beam. So stay connected. Thank you for watching this video.